Scatter plots, correlation, and regression. Correlation, the key word here if you look at it. Correlate. Is there a relationship between two variables? Does one affect the other one? Or is it an association of the two? Linear correlation is when they follow like a straight line pattern. Do they both go up as one goes up, one gets bigger, the other one gets bigger, or do they follow like a decreasing pattern? Or they could be a constant. It's a possibility. If you have had algebra, then you know what I'm talking about. Now what we're going to do is we're going to use scatter plot. So we've collected some data and we're going to see, and we're going to plot those points like we would like any pairs of data, like points, x comma y, if you remember that from an algebra class. X is always a horizontal and y is always a vertical. Now with the scatter plots, we do not connect these. And so here's some examples. Now these will, in real life, they very maybe never follow a completely straight line. And so if you see something like this that looks almost like a line, if we were to connect the dots or draw a line through them, it looks almost like a line, that's a very strong linear relationship. This one's kind of hard to draw a line because a lot of scatter going on, so that's a weak relationship, weak linearly. But it does have a linear relationship, which is weak. This one's just a bunch of clusters. There's just a bunch of circles, dots in the form of circles. What it comes down to. So that one you can see there's no linear relationship. And then something that follows like a different curve altogether. This is called a parabola. That's a non-linear relationship. It's actually a quadratic. If you've had college algebra before, so that's a non-linear relationship. The thing is, how can you tell by a picture? Well, you really can't, and so a lot of times you can't. And so what you do is you make a scatter plot, and then we'll use something else here in a few minutes to demonstrate that there is a way to do that, to find a numerical value that represents how close something is to a line or not a line. And so I'm just going to do this scatter plot, and hopefully this won't be that bad. Hopefully just you remember from like a math class of some sort that you had along the way. So maybe bring back some memories, hopefully. And so what we have here, these will be our x values, these will be our y values. Time is normally x, so these will be like years after 1990. That'd be 1991, 1992, 1993, 1994, and then be like 2000. And these are like the money, you can say it's like money that you may earn in thousands per year. It could be anything like that. And so let's plot these. Now notice to go from 1 to 10 on the x-axis. So I'm going to label this x-axis from 1 to 10. Trying to be consistent. What I mean by consistent, having everything spaced apart equally. If you have graph and paper, this would be even better to use. I'm going to erase that thing because it shouldn't be there. Now on this, I see it goes up to 45, so I'm probably going to count by fives. I can count however I want to, but ones will take forever. Let's count by fives. 5, 10, 15, 20, 25, 30, 35, 40, 45. And now what we're going to do is just plot points. So 1 up to 10, so I'll put a dot there. 1 goes up to 10. 2 goes up to 15. I don't like the fact that dot's moving. Hopefully it won't move anymore. 3 goes to 22. So we're going to say it's about right there. 4 looks like it's at 18. These are just approximations. 5 is 25. Like I said, if I had graph paper, would be a whole lot better. 6 is 35. This is the time of the video where I start getting a little slap happy because I'm getting a little bored of doing this. 7 is 28. Oh, my dot moved again on me. 635, 728. 8 is 42. And approximate about right there. 9 is 30 and 10 is 45. 9 is 30 and 10 is 45. So you ask yourself, does that look like it follows a line, a linear relationship? Keep in mind this is time. This would be my money. Money, money, money. So you can say yes it does, because I can like draw a line and it looks like it's following some kind of pattern in there. It's pretty close. I mean, there's some residuals, there's some distance, and that's okay. It's not gonna be exact. The question is how close the line does it follow? And so that's what we're going to find later in this chapter. Maybe not in a few minutes, but we're going to do something else in a few minutes to build up to what we can actually find later in this chapter or this unit, or who's ever watching this video, whatever class you may be in. But it's always good when as years pass by and if your money's increasing per year. That's a good thing, especially if you're in business. Now, my question is there an easier way? Well, of course there is. Have you ever seen StatCrunch? StatCrunch is wonderful. So I've already got the data values in. So if you go to graph, which is always nice to have, scatter plot, and my X variable, I'm going to call that one time, Y variable, I'm going to call it money, and just click compute, and there you go. Is that not the same thing that I just drew? It's pretty similar, isn't it? Look at this. I've also got these numbers in Excel. Excel may be even easier. So all I'm going to do is just highlight these numbers, these values, and then I'm going to go into insert. I should be at home. I'm going to go to insert, and you'll see the scatter plot right there. And then hit that right there, and you'll see it. See how easy that was? And it's got the axis labeled a little bit differently, but it's okay. Works the same way. They got the 5s. There's a count by 2s. That's fine. But it's pretty much the same as I have. So don't be afraid to use technology. It can be a good thing. And so what I was talking about, that there could be something that will provide you more information on whether or not how closely a scatter plot follows the line. That's called a linear correlation coefficient, represented by the letter R. Now that it does involve a messy mathematical formula, which we'll talk about in a different video. But it does measure the strength of linear association between two variables. And the lines can go up and they can go down. And so the values are all between -1 and 1. If it's a -1, that means the line has a negative slope. So it's going down. And if the line's going up, always read left to right. It's a positive slope going up. And that's what the signs tell you what direction. Negative is down and positive is up. Closer is the 1, the more of a line it is. So 1's the key. 1's the key. The closer to 1, the closer to the line. Closer to, I just say plus or minus 1. Closer to plus or minus 1, stronger than the line. The formula is messy. And I'll show you that in a different video. I'm not actually, it's too messy. I'm going to use technology. So here's a little diagram that helps out a whole lot. The closer R is to 1, if it actually becomes a 1, then it's a perfectly positive linear relationship. And if it's exactly a -1, then it's a perfectly negative linear relationship. If it's 0, there's no linear relationship. And so one thing we can do is we use a table of critical values of R. And these are actually based on, I think, 95% confidence. And so what it says is blah, 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 blah. But this is what's going on. These are the critical values. We'll use these. We'll use sample sizes for now with these. Later on we won't have to. But for now, these are the values that we're going to use. And these are critical values. So what you're going to have is you're going to have critical values. We're going to label these plus or minus based on the sample size. And then there'll be an R value. Linear correlation that comes from actual data. And what we're going to do is we're going to see if it's in this region or in this region. If it's in the extreme, in other words, if it's greater than the critical value or less than the negative of the critical value, then there is a correlation. If it's in between, there is no correlation. So we're using these. It's a lot like the bell-shaped curve kind of thing. These are extreme values. So anything that's in the tails, we're not expected because it has such a small probability of occurring. So, and if they do, that means they're significant. And they're in the middle. Well, we expect things to be in the middle. So that's not really unusual. And so let's just do a couple examples so you can see how this works. And here's what I was just saying is you can also use absolute value, but just look at the right side if you want to. So if it's greater than the critical value of R, I know that there's things you gotta watch out, but as far as variables go, this linear correlation coefficient for this example is R equals 0.776. So that's the actual R value from the data. And then these are from the table. So here's how you do this. I'm going to draw that little diagram. Remember, these are extremes. These are good as far as correlation, and this is not good as far as linear relationship, because these are closer to 1. Either way you look at it. And then this is like a 0, so which means there's no linear correlation. See that? Correlation, correlation, no correlation. So here's how this works. I see we have 12 males, and I come to this table and I see this 12. So that means this right here is 0.576. This critical value is, and this one is negative 0.576. And once again, I'm going to go up here to show you 0.576, negative 0.576. These are the critical values. And then the R value is 0.776. If I were to plot that 0.776, I would put it somewhere over here. Since it is in this region, what can you conclude about linear correlation? That there is evidence to support. Evidence. I'm just going to type that out because that's not going to be nice. And hopefully I can type it out without causing any issues in this video. Hopefully. But evidence does exist to support a linear correlation. You can think of it like that. Got that? That's what we're testing. Support the claim of a linear correlation. So we're going to find evidence to support, or we're going to conclude that there is not sufficient evidence. So let's look at this example. And I'm going to use the same chart because it's a standard chart. Going to draw my little picture. I better use those endpoints. 1 and -1 as high as we can go with the R value. And so 8 males, that means I'm going to use this. And so I'm going to mark them off here and here. So it's going to be 0.707 and then -0.707. And then my R is 0.306. Remember, that's good. That's sports. And here, there's no evidence to support. And so 0.306 is here. Be right smack down in the middle of 0. So it'll be right here. which means it's in between, which means that's not good. You can always think of it as, well, since it's in between and it's not greater than, what that means is, I'm just going to copy and paste that so you know, there is not sufficient evidence to support. And that's how you use the chart, and that's really all there is to it. And if you ever have any questions, just ask.